Hello everyone. In this video, I want to show you something really interesting. So, the other day I was talking to my students in Rapid Prototyping Lab and they printed this amazing toy, which you can see now. And this is a rooster that walks down the slope by itself without you doing anything. And all this rooster has is one of the legs that is like a pendulum and the other leg is fixed. So I asked them to print one for me, and I knew this is really complicated, so I decided to make a video and explain it. But before that, let me show you this cool, I would say, educational toy, and then we're gonna explain how this guy works. So here we go. Look. There we go. Okay, cool, huh? A rooster that is taking steps and basically going down the slope. So, a robot like this is what we call a passive dynamic walking system or walking robot. First of all, it's passive because you don't need to really use any power. And the way that it works, of course, the energy for it is potential energy. So it has to work on a slope. So gravity does the job. And of course, it's a dynamic system because, as we'll see, it is basically a double pendulum, as you can see, where one of the leg is fixed and the other one leg is basically the one that can swing forward and backward like a pendulum. Okay, so as I said, it has two legs and they are connected by a friction hinge at the hip. So to show you that here, let me take this guy apart for you so you can see basically all it has is, there we go. So this is the rooster, right? And this is that basically leg that is the pendulum, correct? So it oscillates forward and backward. And this is your frictionless pivot. So you see that the pivot has a little bit bigger diameter than the hole has bigger diameter than the pin. So there is not really much of friction here. And so here we're gonna go ahead and put it back on, right? So this is the system, extremely simple. And to make sure that it doesn't slide and just goes down, here you see my students added two patches of sandpaper and tape it to the bottom of the feet. Okay, so we have one leg that is fixed to the body. We call it basically the stance leg. And we have another one that is swinging, and that is called the swing leg. Okay, so that's all it is to the structure of this robot or this toy, basically. So as I said, it works like a double pendulum, right? So this is one object, this is the other object. Now, the only difference is, as opposed to a double pendulum that we see typically in textbooks, in double pendulum, one of the members is pinned down to the ground like this, and the other one is pinned to mass number one. In this case, this fixed ground link does not exist. Okay, so it comes down here and there is this connection that it touches the ground. Okay, so there is no fixed link as opposed to the other one, but it is actually a double pendulum. And the simple way to model it is to assume that the masses are at the ends of the object, but the reality is, that the mass is a spread. So here, to make it simple, we assume that the masses are concentrated. The bigger mass, capital M, is the mass at the hip, right? So it is going to be right here. And the other one at the foot, which is here. And the length of these legs are basically You can assume that they're both the same L, right? And they are rigid masses. And the pin here is a frictionless pin. Now, here we let it go down a slope by angle gamma. One very important thing about this gamma is if the angle is very small, like only 1 or 2 or 3 degrees, something like that, your system might stall. So you can see even right now, I need to give it an initial kick to go. It can stand on the system and not go down. And if the angle is too big, then it can topple forward. Okay, so one of the things is for the mass and the geometry that you design your robot and the width of this legs, you need to make sure your angle is reasonable. And you see here, my angle is not even 30 degrees, but it's also not like 2 or 3 degrees or something. Okay, so this angle should also be in a reasonable range. I would say typically below 30 degrees or so, and maybe above 10 degrees, 5 degrees, 10 degrees, I would say is a good angle. Now, the way we define the angles, so the stance angle or theta is the angle measured from normal to the surface and the stance leg. So in this case, this is normal to the surface and this is the stance leg. So that is the stance angle. If your leg is perfectly perpendicular to the surface, it's 0. If it's tilting forward like this, it is basically positive. The swing angle phi is, in this case, you can see it is measured from the stance leg. If the swing leg is behind the stance leg, like in this case, phi is negative. If it's in front of it, like in this case, that is a positive phi. Okay, so these are your 2 degrees of freedom and your generalized coordinates, phi and theta. And you can see that the angle between the legs is actually phi, the swing angle. So what happens during one step? As it takes one step, what really happens is the stance angle slowly changes when the hip moves forward, but the swing angle basically changes faster like a pendulum until the swing angle touches the ground. And here you can see that in the case of this rooster, your front leg, which is the stance leg, as it goes like this down the surface, right? Let me put it up here. So this one, if you look at it, it changes a little bit. But this one in the back, the swing leg, basically changes a little bit more, okay, and changes faster. And now there is a difference between this rooster and the model I'm showing you. In this case, the swing leg always stays behind the stance leg. In other words, in this case, phi angle is always negative. This guy cannot pass and go to the front, this back leg. It always stays back. But the essence is the same. So here, look, the swing leg is the contact point. When it tilts forward, the stance leg becomes the contact point, and then it goes like this, and then like this, and it keeps going. So the fact that they keep changing as being the contact point, that is the same for this one, which has mechanical limits on the swing angle. The swing angle always stays in the back. And the one that I'm showing you here in this schematic, you see that your swing angle can go in front of the stance and phi becomes positive, but that doesn't work for this rooster the way it is designed. So during the heel strike, as I said, the swing foot hits the ground and the role of phi and theta swaps because the contact point is swapped. So if we want to look at the assumptions of the model, we assume that the two legs have the same length L and they are both rigid objects. The mass distribution, there is a bigger mass M at capital M at the hip and a smaller mass M at the foot of the swing leg. and the rest of the objects have no mass. Again, this is not the case for this rooster. There is here rigid body with distributed mass. So here, this model that you see and this modeling that I'm about to show you using Lagrangian method is a very simplified version of this rooster here. This is a little bit more complicated than this model. And the coordinate frame, of course, we are using is the x-axis is downhill along the slope and y is normal to it, upward. And your generalized coordinates are, of course, phi and theta. So if I want to show you the coordinate system, in this case, the y-axis is along the normal. So it is exactly, let me use an arrow. Let me see if I can insert an arrow because I might not do an amazing job here. So this is your coordinate frame, and you see that the hip point is right on the y-axis. Now what I need to find are the positions for the end of the stance leg and also the foot for the swing leg and the hip joint, right? So we need to find these coordinates, especially these two. I mean, like these two are the same thing. So here you can see that if I want to find the location of the hip joint, right? So clearly you can see that if the length of this member is L, right? So this is also L, then the y coordinate is clearly L cosine theta. So this distance from here to here, that is L times cosine theta, and this distance from here to here in the x, this is L times sine theta, correct? So clearly the location of the hip is given by L sine theta and L cosine theta, which is exactly what you can see. This is where one of the masses are, the capital M. And the swing foot, that does depend on the angle phi. So you can see that basically from the hip joint, which is this point here, so this is x of the hip and y of the hip. From that point, you need to calculate two other distances, right? And they are basically given by this L, and let me clean this up a little bit. They are basically given by this L and by this phi. So you need to move back in the x direction by L sine phi, and in the y direction you go down by L cosine phi, assuming that here the phi is negative. Now if it's positive, the x of the swing point becomes bigger than x of the hip point, and the y of it still below. So to do that, we need to add L sine phi and negative L cosine phi to x of the hip and y of the hip, right? In that picture that I showed you, phi is negative, right? Look, in this picture, as I said in here, phi is negative. Therefore, a sine of phi, which is negative as well, look, when you add that to the x of the hip, this is a negative term. So x of s is going to be less than x of the hip, and it's going to be behind it as it is. But for a negative angle, cosine is still positive. So this guy is also negative, and therefore y of the swing point is also below y of the hip point. Yes? So these are for a negative phi, and if phi turns out to be positive, this guy still stays below, but this one now becomes a positive term. And so x of the swing point becomes bigger than x of the hip, and it moves forward. In this rooster, that doesn't happen because your phi in this case always for this rooster is a negative angle. So this is the location of the hip joint and the end of the swing point. These are where the masses are, small m and capital M. Also, for potential energy, as you know, we need to know the absolute elevation. So we need to know if we are here at a point x and y in this coordinate frame, right? So this is y and this is x. If a point is x and y on this surface that has this angle gamma, what we really need is this absolute elevation z, to basically calculate the change in potential energy. And since the XY frame here we have, and the traditional XY, which is horizontal vertical, have a rotation gamma between them. So if I have X and Y, and gamma, Y cosine gamma minus X sine gamma is going to be the elevation from the upright position, and that is the base for calculating the potential energy. So now, assuming that we only have concentrated masses and using these two generalized coordinates, we are going to use the Lagrangian method. So we need to calculate the velocity of the hip joint and the bottom of the swing foot. So we take derivatives from X of the hip and Y of the hip. We take time derivative using the chain rule, basically. The derivative of L sine theta becomes L cosine theta theta dot. The derivative of L cosine theta becomes negative L sine theta theta dot. And then we similarly take time derivative from X of the swing and Y of the swing, and we find the X dot and Y dot. Then I'm going to square both of these and add them together to get the velocity of the hip joint squared. And using sine squared plus cosine squared equal 1, I can show that the velocity of the hip point is going to be L squared theta dot squared, and the velocity squared of the swing point is going to be this total term together. And so the kinetic energy, since I only have point masses, is 1/2 capital MV of the hip squared plus 1/2 small MV of the swing squared. And that is going to be this, where here the sigma is the sum of the two angles. So here we define a new angle sigma. Let's see that I mentioned it down here, but I should have brought it up. So sigma here that you can see is sum of the two angles, phi plus theta. So this is my total kinetic energy in terms of this sigma here. And then for potential energy, I just showed you that the potential energy comes from this Z. So all I need to do is to multiply the Z of the hip by capital M by G. So this is the potential energy for the capital M mass. And then for small mass, I use the small m times G times Z of that point. And the only difference between ZS and ZH is their X and Y points, right? Because for Z of S, we use X of S and Y of S. For Z of H, we use X of H and Y of H in that formula, Y cosine gamma minus X sine gamma. So this is Z of the hip, absolute height of the elevation of the hip. This is the absolute elevation of the swing point. And so I add them together and I get this guy here as my potential energy. Now I subtract kinetic and potential to get my Lagrangian. And once I do that, now I have to apply the Lagrangian equation here for each Qi. So here, if you want, I can use Qi, where Qi in this case is either theta or phi. Okay, so I have to write this one time for theta, one time for phi. The other thing we need to pay attention to is the right-hand side. This right-hand side is the non-conservative generalized forces, or torques in this case. And in this case, there is no generalized torque because the pin at the hip is frictionless. Okay, if it was friction, then clearly we had to add terms here. But here we assume it's frictionless, so the right-hand side is 0. And for that, basically, we can model it in much simpler ways. So here you can see the derivative of the L, or the T, basically is calculated with respect to theta dot or phi dot. If you want, you can write L. It doesn't matter because V is not a function of theta dot anyways. So these are the partials with respect to the velocities. And then I have to take time derivative of them using the chain rule. And then I need to find the second term, which is the derivatives of the L with respect to theta and also with respect to phi. So let me just change these to L instead of T and V. And here are the derivatives with respect to, now here it didn't T and V, so it can do the separate ones, right? So here you can see that actually the reason is that it's done like this is, so in order to calculate this term, which is partial of L with respect to phi or theta, you need partial of t with respect to theta, partial of v with respect to theta, and then both of them with respect to phi. And these are those terms here, okay? So you have to subtract now. You have to subtract basically this one minus this one. That is going to be the partial of L with respect to theta. And then when you get this one and you subtract, you are going to get partial of L with respect to phi. So now you have the second term. The first term is also created. And you plug them into both equations, assuming the right-hand sides are 0. And guess what? Here are your equations of motion. So this is your first equation of motion. This is your second equation of motion. And if you want to write it in a linear manner, so in terms of q double dots and in terms of the C matrix and the gravity term, this is what you have. So this here, this matrix, which depends on the sigma angle. Remember, sigma is phi plus theta. So your M matrix or mass matrix, or in this case, the inertia matrix here, is clearly not a constant matrix. It does depend on both angles. And this term here that involves your Coriolis terms and centripetal terms, clearly you can see that again is variable. So this is your C of q dot times q dot. And then you have your gravity term here, which is G, and clearly, again, it does depend on the angles. So these are your equations of motion, these two, and you can see that exactly it is similar to a robot. It is in the general form of any robot, with the right-hand side being 0 because it's a passive robot. So this is the equations governing for one step. Yes? Now, another thing that we have to pay attention to is during a step, we assume that the stance foot is stationary at the origin, okay? So basically, if I go back here, you can see that now it might not be correct to say at the origin, but above the origin. So basically this point here, we assume it is going to stay there, and it's this guy that is swinging back and forth. So here you see I edited that here as above the origin. Now what happens during a hill strike? So the swing foot touches the ground. The y of the swing becomes 0, and remember, y of the swing requires that L cosine theta minus L cosine phi to be 0. That means cosine theta should be equal to cosine phi. So when those theta and phi are changing, starting from some initial condition and initial velocity, whenever this condition happens, that means that the swing foot will hit the ground and you have a strike condition. And here you can see the y of the swing foot here again, right? So it's y of the h minus L cosine phi. So it's this one. And when this is 0, that means these cosine terms have to be the same, okay? So that is the condition for strike. That is when the contact point switches from one leg to the other. And that is when you have to swap the two legs, okay? Now, let's talk a little bit about this swapping the legs. So what kind of impact are you talking about? What kind of collision? It hits somewhere, so we are talking about an impact. What kind of impact do we assume here? We assume the impact is perfectly plastic and with no slipping of the swing foot with respect to the ground. Now, to assure that there is no slip and is perfectly plastic, that's why you see that my students use these sandpaper patches and attached it to the bottom of the feet, because if it's just plastic against plastic, you will definitely have some sliding. So here these patches are to assume that, to make sure the assumption of no slipping during impact and perfectly plastic impact, that does work. Now remember that we said during an impact the legs will swap. So the swing leg that will hit the ground, right? This one that is hitting the ground, it will get the same velocity as the ground, or in this case, the slope, and the slope was already stationary. So the swing leg, since it's perfectly plastic, will get the same velocity, which is 0. But right after this is when they swap. So the swing leg now becomes the stance leg. So the new stance leg, or I can say the former swing leg, should have immediate 0 velocity after the impact. Now let's look at the formulation of that. So here we are going to look at the swing foot velocity, and we can define it using a Jacobian, right? So we can say that the velocity of the swing foot can be given by a Jacobian times vector q dot, where in this case this vector q dot is basically like theta dot and phi dot, correct? This is your generalized velocity vector. So you can write it like that. And the components of it are, of course, the partials of the velocities of the swing point with respect to theta dot and phi dot. And so you can write it that way if you want, using a Jacobian, and you can write a similar Jacobian for the stance leg. But here, in this case, we just want to focus on the swing one. So now we want to look at the impulse equations, something that I have never done for a robot in the past. So I want to take a look at it with you. So if you remember, the impulse and a linear momentum equation for a mass was the integral of the force dt is equal to the change in linear is equal to mass times velocity position 2 minus mass times velocity position 1. Now here I would call this impulse, which is integral of force over time. This one, in this case, I call it P. So this is your linear impulse. Now P equals to mv2 minus mv1, okay? Yes? Now, you know that your V here, this guy is your V is J transpose times Q dot, and this is your M. Now here you don't have a single M, this is a multi-DOF system, so instead of small m, you have to use the mass matrix, okay? And instead of V, you can replace it by J times Q dot. So if you want to replace the right-hand side, okay, instead of replacing the right-hand side, this is going to be like the mass matrix times V2 minus V1. And as I said, for V2, I can replace it by J times Q2 dot minus Q1 dot. But here, instead of 2 dot and 1 dot, I call them Q dot plus and Q dot minus. And plus and minus are before and after impact. So this one is going to be Q dot plus and then minus J times Q dot minus, basically. And then if you use a J transpose on both sides, you can basically write it this way. So you can say that M times Q dot plus minus Q dot minus is J transpose times P, right? So you are changing your forces, the integral of forces versus time, you are taking them to the Q space by using J transpose. And now that kind of impulse that you have in the joint space is equal to the change in the momentum, but in the joint space. So if you want to write it, it's mq dot plus minus mq dot minus is J transpose times P. So this is your impulse momentum in the Q space. Good. Now, remember this J here is the one that relates the velocity of the swing point for you to the generalized velocity vector. Now, your no slip condition is that the velocity of the swing point after impact should immediately be equal to 0. So J times Q dot plus should be equal to 0 because it is a perfectly plastic impact and with no slipping condition. So how do I use these equations together? The way that you do it is you try to solve for q dot plus in this equation. So if in this equation I want to solve for q dot plus, the way you do it is first you multiply both sides by m inverse, and then you take this negative term to the other side, so it becomes q dot minus and then plus m inverse times j transpose times p. Yes? And that is exactly what you can see here. And pre-multiplied by j, this should be equal to 0. And now what? Now you multiply j by both sides and take this jq dot negative to the other side, and you get this one. So this is the same as saying no slip condition, right? Or zero velocity immediately after impact for the swing, the former swing foot or the current stance foot. Yes, so this is basically the no slip equation. Fine. Now, how can I use this? Because remember, the goal is to find q dot plus. The goal of looking at impact is to know q dot plus given q dot minus. If I know my theta dot and phi dot before impact, how much are they after impact? So how can I use this equation to look at my update in the joint velocities due to impact? Well, all you need is to basically solve for the impulse vector p here, because remember, p is not something that is given to us. Okay, we don't know the impact forces, so the only way we can use p is to use the no slip condition. So here I'm going to solve for p from this equation. So p is clearly going to be basically j m inverse j transpose, correct? And then the inverse of all of this with a negative sign multiplied by j and q dot minus. So this is the p. I find it from here, yes? And then what? Once I find it, I'm going to take this p and plug it right back up here. And I can plug it here actually. Instead of there, it's better to directly go here. I plug it directly here. And there we go. Now I get q dot plus equals q dot minus plus m inverse j transpose times p. And that is m inverse j transpose. And p has this negative sign. And it has j m inverse j transpose inverse times jq negative. There we go. So finally, after all of that, this is my important equation, this one. This shows if I have the velocities, the joint velocities before impact q dot negative, how to find them after impact, or what? Q dot positive. So this is how to formulate the transition of the joint velocities due to perfectly plastic impact. And if you want, you can factor out a q dot negative out of this. And so one of the terms will be I minus that. And that is another way to write it. So we can write q dot positive as this whole matrix times q dot negative, I minus all of that. Okay, so this is, you can do it as a matrix, one single matrix multiplied by it. And then after, as I said, once the impact happens, now you have to swap. You have to make the stance leg the swing and the swing the stance. So the way you can do it is, again, you can do it with a simple matrix multiplication. You can say that q dot new is a relabeling matrix times q dot positive, right? And q dot positive is the velocities after impact. And the relabeling, if you look at it, it is the relabeling matrix is 0, -1, -1, 0. And what does this one do? what this one does is, first of all, you see that as opposed to an identity matrix where on the diagonal is 1 and elsewhere is 0, it's swapped. So zeros and ones are swapped. That will make theta dot and phi dot to swap and also give each one of them a negative sign. So now I can say theta nu is negative phi and phi nu is negative theta. And the reason for this negative is because they are swapped. The reference is also swapped. So if the theta was on one side of the vertical to the surface, now it is going to go to the other side of it. So if it was positive, now it's negative, and vice versa for phi from theta. Okay, so you need to give them a negative sign and swap them, and that can easily be done by this relabeling matrix. So what we really need to do to simulate this system are 4 major equations. This is your equation number 1, or equations 1 and 2. These are governing the change in theta and phi between the steps, right? So as the leg swings, this is the first one. When this condition happens, which is your equation number 3, when this thing happens, then you have to first calculate the velocities after impact. So at this point, the q dots that you have is simply q dot negative. At this point, what you have is q dot negative. That's all you have. But after the impact, these are the q dots that you're going to have. And finally, now you have to swap them. So now you use this equation as well as this one here, basically, to swap the velocities and the angles, both of them. So here we go. And I can call them 5 and 6. So equations 1 to 6 are basically everything you need to simulate the system. But this time I decided, instead of showing you a MATLAB simulation, which I'm sure at this point you can do yourself, I show you the physical system, the rooster itself, and show you that, hey, behind the scene of this simple looking toy, actually there is a world of dynamics hidden, and deriving the equation of motion for this simple toy is actually not as simple as you might think. So just as a last time, let me just go ahead and run it for you. So now you don't look at this as a simple fun toy anymore. You are now looking at this as something really complicated as well, although it's still fun and beautiful to watch. But now you know how complicated it is just to describe the motion of this simple toy. So this is called the passive dynamic walking robot, or bipedal. This guy is a bipedal robot. It just has 2 legs. And one last thing I want to mention before I finish this video, remember that if you watched under my playlist Dynamics, I talked about the double pendulum. You know that a double pendulum is chaotic. Okay, and chaotic means if you change the initial condition, the response of the system will be completely different. And it's very sensitive to initial condition. And that's the same here because it's a double pendulum. So if you start this rooster from a little bit different angles and different velocities, the way it behaves is not going to be the same as if it was a little bit different. And of course, it does depend on some parameters in the system. Not for all parameters, the system is necessarily chaotic. If you want to know more about this chaotic behavior of the system, I refer you back to the paper that I mentioned in the beginning of the video, this paper here, New Walking Dynamics in the Simplest Passive Bipedal Walking Model by Leah and Yang, that I said I got my picture from. I refer you to this Elsevier paper. So once you go through this paper, they talk about it, they talk about the modeling of it and so on. And here you can see the bifurcation diagram for the system. And you can see that the system does show bifurcation and it does show chaotic behavior. And here you see they have created Poincare map and other things, and they talked about different gates, okay? So different periodic behaviors and different things, okay? You see, so here one of the things they have is gamma, basically the angle of the surface can show different responses in the system. And that's one of the things I mentioned, that this angle will definitely uh, change the behavior of the system. So gamma here, you can see that the surface angle is very, very critical. And again, here you can see all about the chaotic behavior, the Lyapunov exponent, and so many other things. So if you want to know more about it, watch this or look at this great paper. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.